Hello everyone, this is the fifth and last lecture on the subtopic surface tension, and here we are going to discuss excess pressure over a curved surface. So welcome to IIT-JAM in chemistry tutorial number 28, and this is the lecture number 6 of the physical chemistry chapter, liquid state. So have a look on this picture. Here is, in a container there is some liquid and a capillary is inserted in it, dipped into it. Then this portion must have some excess pressure, and we have just calculated from the hemispherical depression the pressure P2 minus P1 is P prime, and that is twice gamma by R if gamma is the surface tension. So if the pressure of the liquid are different in these two parts, then what about the pressure of the vapors above the meniscus and above this surface, flat surface? The pressures are also different, and we have to calculate the ratio, the difference in these two pressure of these two parts with the help of surface tension. Now it has been assumed to be a hemispherical depression, therefore the radius of curvature is actually equal to the radius of the capillary. So let's describe first P1. This is the pressure of the liquid at the bulk, and this is the pressure of the liquid at the capillary, that is below the meniscus, and this pressure must be greater than this one, and we know the difference of these two pressures is actually the excess pressure at the meniscus, that is the pressure due to hemispherical depression, and this is nothing but equal to twice gamma by R if gamma is the surface tension of the liquid and R is the radius of curvature, that is the radius of the capillary. Now the vapor above the bulk is P0 and the vapor above the meniscus is P. Then this pressure P must also be different from this one. So we have to take into account these two things and calculate what about this pressure P, that is the vapor pressure over a curved surface. So P0 is the vapor pressure above the bulk surface, and P the vapor pressure above the meniscus. So what about the pressure change? The pressure changes for the liquid from P1 to P2, and for the vapor P0 to P. So P1 to P2 for the liquid, and for the vapor phase it is P0 to P. Now the molar volume of the liquid, it is V bar, and suffixed L means it is indicating that of the liquid. Similarly, molar volume of the vapor is this one, V bar, and in the suffix there is V. V stands for vapor. So after denoting the molar volumes, we have to denote the pressures of the corresponding phases also. For the liquid phase, if the pressure is PL, for the vapor phase the pressure must be PV, and the corresponding changes for the liquid phase, that should be dPL, and for the vapor phase that should be dPV. Now we have four fundamental equations of thermodynamics where the energy changes have been formulated as a function of different state functions, such as what is the value of du, dh, dA and dg. So we know the relationship about dg, and this is minus s dt plus v dp, where g is the free energy, dg is the free energy change, s is the entropy, t is the temperature, v is the volume, p is the pressure. We know all about this. Now if this is the equation regarding Gibbs free energy, then molar free energy change is the change in chemical potential. So if you divide both sides by the number of moles, then G by N becomes mu, so dG becomes d mu. So that becomes the change in chemical potential. Entropy, if you divide entropy by number of mole, then it becomes molar entropy, and if you divide volume by N, then it becomes molar volume. So the equation becomes d mu equals to minus s bar dt plus v bar dp, and if you keep the temperature constant, then dt part vanishes, so the equation becomes d mu equals to v bar dp. So this is the equation. So we have to apply this equation for the changes in the liquid phase, for the changes in chemical potential of the liquid phase as well as in the vapor phase due to their changes in pressure. So changes in chemical potentials due to changes in pressure are, for the liquid phase, it is d mu L, it is V instead of V bar, we have writing here BL bar dPL, and for the vapor phase it is d mu V, and instead of V bar we are writing here VV bar, that is the molar volume of the vapor phase, into dPV, that is the pressure change in the vapor phase. And at equilibrium these two must be equal, okay, and hence the right hand sides would also be equal. Therefore at equilibrium the right hand sides of the previous two equations are equal. That means V molar volume of the vapor into change in the pressure of the vapor equals to molar volume of the liquid into change in the pressure of the liquid. VV bar dPV equals to VL bar dPL. Now we have to integrate these two equations in both sides. And what should be the limits? The limits should be P1 and P2 for the liquid phase and P0 and P for the vapor phase. This is the lower limit for the liquid phase. This is the upper limit for the liquid phase. This is the lower limit for the vapor phase, and this is the upper limit for the vapor phase. Okay. So let's integrate both sides giving limits. Look, in the vapor phase, lower limit is P0, upper limit is P. In the liquid phase, lower limit is P1, upper limit is P2. Now we have to make one more assumption, that the vapor behaves ideally. So we can apply the ideal gas equation. So in place of, we know PV equals to nRT. So PV must be equal to RT for 1 mole of gas, and if it is 1 mole of gas, then it becomes molar volume. So V bar equals to P into V bar equals to RT. Therefore V bar equals to RT by P. For the vapor it is VV bar equals to RT by PV. So we just put this value in place of VV bar, we have put RT by PV. So here RT by PV is appearing here instead of VV bar. And now the integration is proceeding as follows. So what is the result? RT is constant because temperature is constant. Then dP by P means ln P. So ln P with limit P0 to P must be ln P by P0. And in the right hand side, simply just VL bar, it's a constant, and at a constant temperature this is a constant. So this is taken out of the integration. So the integration only for dP. So the value of P must be limited from P1 to P2. That means P2 minus P1. And we know this value P2 minus P1 is P prime, that is twice gamma by R. So let's put this value in place of P2 minus P1 as twice gamma by R from the equation of hemispherical depression, and we are showing this relationship here for our convenience. And just rearrange the RT part, taking the RT part in the right hand side, thus getting equation number 9. And in place of VL bar, we can also put another relationship, capital M by rho. Capital M is the molar mass, rho is the density. So if molar mass is divided by density, then molar volume is obtained. So in place of VL bar, we can put the molar mass of the liquid divided by the density of the liquid, and thus equation 9 becomes equation 10 in this form. ln P0 by P equals to twice gamma capital M over rho capital R capital T small r. We know the physical significances of all these parameters: gamma surface tension of the liquid, M molar mass of the liquid, rho density of the liquid, R universal gas constant, T is the temperature, R is the radius of the capillary as well as radius of the curvature, P0 is the vapor pressure over the bulk, and P is the vapor pressure over the meniscus. And this equation is also applicable for the liquid droplets. That means where you have a single surface, in that case curved surface must have vapor pressure relationship like this, equation number 10. So let's discuss one question. The fact will be clear to all of you, and that is question number 7 as a continuation from the previous questions. The relation natural log of P0 by P equals to twice gamma capital M by rho R T small r for vapor pressure over a curved surface. Now the parameters have been described here. P0 vapor pressure over a planar surface, P vapor pressure over a curved surface, the curvature formed due to surface tension, gamma. M is the molar mass of the liquid, rho is the density, R is the universal gas constant, T is the temperature, and R is the radius of curvature. So this is applicable for which situations? Hemispherical depression, liquid droplet, free air bubble within a liquid. Now you see that this relationship is applicable for the curved surface with a single surface where excess pressure is twice gamma by R. Now look, for a hemispherical depression there is a single surface, single curved surface. For a liquid droplet there is also a single curved surface. And here air bubble within a liquid there is a single curved surface. But in the option C, for a free air bubble, there are two surfaces. One is inner surface, another is outer surface, where the excess pressure is 4 gamma by R. Therefore, out of the 4 curved surfaces, only a free air bubble has 2 surfaces where excess pressure is 4 gamma by R. So 3 answers are correct here. This is some kind of MSQ type of question. That means you have multiple answers, multiple correct answers. So here you have to tick in 3 options, A, B and D. So that's all about surface tension. The next subtopic in our lecture number 6, we are going to discuss viscosity of liquid. So till then, thank you and have a nice day.